record. All right, so let's try this one. I need to share my video camera here or phone and connect it. And while that's connecting, let me jump back over to the problem. All right. Hey, good. Yeah, this would be a good one to do here. All right. So let's talk here. I guess this is getting into week 5. Wow. Time goes quick.
Already in week 5. It's crazy.
Wow. Yeah. Okay. So week 5 here. All right. So calculating net force. And one thing I should begin this for you and for anybody else who listens to this later on is that this is really where that whole chapter 2 on vectors really comes into big play. You saw it already in last week we did 2 dimensions. You didn't see it when we did 1 dimension. And so I think sometimes in chapter 2, students kind of lose focus or reasoning. Well, why am I doing all of this? And I think you began to see it. But anyways, I'm just going to say that now that probably one of the very first things to do, and I am just going to even start that way, and that'll be kind of my hint, is kind of put an X and a Y and split my paper down the middle because we know that X's go with X's and Y's go with Y's. And so one of the things that I'll just repeat here that hopefully you got out of chapter 2 was that you got to get X components and figure out what those are before you can add them together. And I think you see that here because it says here, 2 forces act on an object. And maybe down lower on my page, I'll kind of draw a picture of this. So I'll call this the X-axis and this the Y-axis. And it says a force of magnitude F1 at a direction of 120 degrees. Okay, so I guess they don't tell us F1. Oh, and that's going to be one of the questions. Okay. But the 120 degrees, and I'm sure from tradition, is the tradition where 0 is the x-axis, positive is counterclockwise. So 120 kind of points off in this direction. And I'm not sure how big to draw the arrowhead because they don't tell me. So I'm just going to draw kind of a solid line for a little bit. Maybe I'll even put, to remind myself, well, this is 90, and so this would be 30 more. The whole thing's 120. And so there it is. Now, force number 2 is a force of 101 and is at 315 degrees. Okay, well, let's see, 90, 90, and 90. So this is 270 going down. 270. No, I'm sorry. 270. Then we got another 30 and another 15 to get to 315. So that's 45 actually down. I think that's a negative 45. Let's see, 315 and 45 make 360. Yeah. So I'm just going to point down at 45 degrees and call that 101 newtons. Okay. And that's something else that's new here, maybe, is that the units for force in the metric system are newtons. So 101 newtons at an angle of 315, or I like to call it a negative 45, but either way. Now it says the net force on the object has an X component of Fx, and so we don't know what that is, and has a Y component of 34.5. So going up 34.5 on my scale. Let's see. So if this is 101, it would be about a third of this. So it's going to go up about this high somewhere. Now, I don't really know the x component. So if the x component was positive, it would come over to here and then up, and it would be something like that. But I hesitate to draw anything. If the x component came out to be 0, then it would just be straight up. The x component comes out to be negative, I guess it would go negative and then up. I just know it goes up. So I better not try to draw anything here. And I still don't know how far to draw this crazy one. Okay. But here's the idea. So let's come back to the math. What this is saying here is when you do the x component, the x component, and I'll put f total, is the x component of the first and then the x component of the second. And then likewise, the y component total is the y component of the first and the y component of the second. Okay, now I'm going to start with the y component. Don't really know, but don't really know which one would be more appropriate first. But I do know this, that they tell me the total y component is 34.5. So because they did that, I kind of feel like I have more information with the y components. That'll kind of be my hint to say, let's work on that one first and see where it gets us. But like any problem solving, you never really quite know what direction to take. In fact, I got a really good question today in the second Zoom that was kind of asking me, well, then how do you do these? What direction do you know to take? And I did a terrible job answering it. I was fumbling around. You don't. What I wish I would have said is, really, you don't. You fumble around. You see what you do know, and you go as far as you can with what you do know. Then maybe you go another direction, and eventually, by keep analyzing what you do and you don't know, you know what to fill in with the missing pieces. So I wish I would have said it was kind of like if you've ever done a jigsaw puzzle. You pour out all the pieces. Maybe you turn them all over. You don't even have to turn them all over. Some people will, some people won't. Some people will find the edges and make the frame. Other people will find everything that looks white and look at the picture and say, well, there's only one place on this picture that's white. Maybe it's like snow-capped mountains. And so you go to that approach. So there is no one approach. You just kind of working with what you do know. And you get better with experience. So I'll say that now in case anybody who listened to that one is asking again. And so same thing here. I don't really know what approach to take, but I do know that I have vectors, so I do know I need x and y components, and I know a little bit more about the y one, so I'm going to go that direction. And I'll say it again. I picked this one because I know the total. So let me do the y component of number 1. Now, the y component of number 1, coming back to this picture, it's 30 degrees from the y-axis. Okay. So I'm just going to kind of point at it and say, okay, how do I get the y components of number 1? Well, I guess it's the magnitude of number 1. And just for picture wise, let's just say it went to here. I really don't know. But if I make a triangle out of this, I would want then the cosine of 30 degrees. I know it's cosine because it's adjacent to the 30 degrees. Now, maybe an easier way, but it has me concerned because it doesn't help you long term, is just to say, well, it's cosine of the full angle of 120 degrees. And that is true. In fact, you can even kind of see that. No, my apologies. I'm looking at the y component. Sorry, sine of 120 degrees. Yeah, that's much better. And you can kind of see if you draw a sine function, it goes up to its maximum at 90 and then 30 more beyond that. And that's the same as a cosine function would do, just that a cosine function would start at its maximum and you would go about 30 down. So 30 down from its maximum, the same as a sine function. So it's kind of your choice here, but for you and anybody listening, I would encourage you to start looking at what math people call a relative angle, not the total angle. So even though the total angle was given as 120, which makes it easy just to say sine of 120, it's really helpful to get a good physical picture. And this triangle kind of helps that I want the adjacent piece to the 30. And I think that's a little more helpful long term. So I'm just going to say in this problem, hopefully you can do both. That you can see that I want adjacent to the 30 degrees, or you could just know from your mathematics class, your trig class, that the vertical component is always sine of the absolute angle. So I get sine of 120 degrees. So whichever one you want to work with, and I tend to like to work with what, again, we call relative angles. In other words, an angle that is under 90 degrees. And that's what this is. This is under 90 degrees. So I'm going to put, if it's okay with you, F1, and I'm going to put cosine of 30 degrees. In fact, I'm even going to grab my calculator here, turn it on, go to mode, check that I'm in degrees, and show you that if I go cosine of 30, I get 0.866. If I do sine of 120, I get 0.866. So exactly the same number. And again, hopefully that rightfully so. But again, I do think relative angles is long term a better option for you than just the 120 degrees. So anything above 90 we can avoid if we look at kind of the picture and do relative angles. All right, well, I'll keep going because the other part of this is the y components of the second vector, which they gave us its angle and its magnitude. And I'm going to point out the same thing. If you just kind of stick to your math class, you might just do this. You might just say, okay, well, the y component of number 2 is its magnitude, okay, 101. And since it's a y component, you can just say sine, and it's all the way around the horn of 315 degrees. That's how you get the y component. You just sine of that absolute angle. All right, now watch this. Of course, if I do sine of 315, I get a negative number. And if I multiply that by the 101, I get a negative 71.4. And so that's true. And it might be the easy way to go at first. But let me just point out another way to get there. I call it relative angles. And I can just kind of look at a picture here. Maybe I'll draw it in green. But getting a good physical picture of what's going on is often what I call the first step in solving a physics problem. And you can see then that making a triangle out of this second vector has an x component and a y component. And clearly the y component is down. So another way to do this would be to say, okay, I can get the y component of number 2 by first of all recognizing it's down. So I put in a negative. Now its magnitude is still 101, but I would want the opposite of the 45. So I'm not going to even worry about the negative. I'm just going to say sine of 45. So again, I might point out that this seems a little harder at first, but it actually is much more helpful long term. And of course, I thought, this is a perfect opportunity to get you to start doing the transaction from one to another. So I thought I better do both. Okay. And so let me just calculate this one and show you that it's the same as this. But notice then that I got the negative, not from the math, but from the picture. And I got the 45 without the negative by, looking at the downward angle. And so I'm looking at the angle less than 90 degrees. Okay, but watch this. So if I put in a negative and I do 101 and I multiply by sine of 45, I get the same number. I get a negative 71.4 newtons. So maybe at this point, doing it the math way might be the way to go. But ultimately, you're really going to want to look at angles always less than 90 degrees, relative angles. And you can even ignore the positives and negatives of them because you would throw that in by looking at the picture. And that's what this is really kind of showing you. But however you want to get the y component, that would go way back up here into this equation. And so this would be a negative 71.4. And as I speculated, by putting in the stuff I know about the y, I have an equation with only one unknown, and I can now solve it for that one unknown. And that's one of the things we're being asked for, which basically is what is the magnitude of F1. All right, so if I put in the 34.5, and then the cosine of 30 degrees is that magical, what is it, root 3 over 2, 0.866. I did it earlier. Let's see if I can scroll up to it. Yeah, there it is. Right there, cosine of 30 degrees, 0.866. Okay. Which should be, actually, I'm just going to test myself, should be the square root of 3 divided by 2. Yeah, root 3 over 2. Okay, and then minus 71. Okay, so now I can get the magnitude of F1. So if I do my algebra here, this is the 34.5. This is then plus the 71.4. Then if I divide that by the 0.866, I get 122.3. So 122.3 newtons would give me one of the two answers that they're looking for. Okay. Now, that means I can really get the second one of two ways. The first way that I started is probably the most logical way for me to do it. Wait. Oh my bad. I misread this. Yeah. Yeah. This is the logical way, and really the best way is, well, I'm looking for the net force on the object, the x component, this total. So what I have to get is the x component of number 1 and add it to the x component of number 2. So let me come back down into my vector picture again. Here's number 1. And now that we know it's 122 newtons long, I can actually put a number next to it, 122.3. But let me make the same comment. There's two ways I can get the x component. I could just put in the 122.3. And if I do what we call absolute angles, I can just go cosine of 120 degrees. That's the technique I call the non-thinking technique. It's just using math. But also, and I'll do this one in green, I think you ought to see the relative angle of this. See, back here when I did the relative angle of 30 degrees and I wanted the y component, I noticed I wanted the adjacent, so I did cosine. And it's kind of interesting that I did cosine for a y component, because if you're just doing the absolute angle, you just put sine of 120, and you kind of do it without thinking. But if you look at the picture, you want the adjacent one, and it's the adjacent one that tells me I want cosine. And so the same thing, if I'm looking at an angle of 30 degrees and I want the x component is opposite. So for me to get the x component of number one, I would have to take its magnitude of 122.3, and I would have to say, I want the sine of 30. I know it's sine because sine is the trig function that gives me opposite, and it's opposite of the 30. And also, look, it's pointing in the negative x direction, so I got to put a negative in there on my own. So kind of like I did down here to get the y component of number two, I had to look at the physical picture to decide the negative and then the sine or cosine function of the relative angle. So I got to do the same thing. So I would agree that this looks a little harder here at first. This is the one that is going to make you look at the physics in order to figure out that, hey, there's a negative sign, and look at the physics or the physical picture to decide if I need a sine or a cosine. And it's not just the traditional, hey, since we want x component, we do cosine. But to convince you that these are the same, and ultimately you'll see to convince you that this format is a little bit nicer, studying the physics, not just plugging the math, is the way to go with this. So I'm going to go ahead and I guess do that. So over here, I got the 122.3, and I'm going to go cosine of 120 degrees. And notice it comes out negative. So it's negative 61.1. And then also, not a surprise it's negative. I'm just looking at the picture, and the y component should be positive and the x component should be negative looking at the picture. So not a surprise it's negative, which also is why I put the negative in here when I was doing this technique. So let me do this technique to get the x component. It would just be the negative that I throw in there from the physical picture, the length of 122.3, which I know, and then the fact that I want opposite of the 30 degrees means I would do the sine function of 30 degrees. And look what I get, negative 61.1 again. So not a surprise. Hopefully I didn't make this extra hard by looking at both methods, but I think you need to see both methods long term. And so the just what I call the blindly plug and chug, just do absolute angle, always do sine for the y component and always do cosine for the x component is great. But a lot of times we get away from absolute because we're not dealing with math on a scale. We're doing a physical problem. We've got ropes that hang and we got pulleys that pull, and we've just got angles that are all relative. And so doing things from relative angles usually is going to be what's going to serve us well long term, because that's really how our physics problems are always going to be. Nobody's going to say, hey, the angle's 315. What you're going to get is something that says, hey, I'm hanging a sign and the rope is angling downward at 45 degrees as it holds the sign in place. And that's the kind of problem you get. Nobody says 315 degrees. So that's why knowing the relative angle, knowing how to do things from the relative angle, throwing in the minus and the appropriate sine or cosine is long-term beneficial. All right, so I did both, maybe making the problem longer and harder than it needs to be. But now let me put those in. Now that I got the x component, which we just said, the x component of negative of the first one is negative 61.1. The x components of the second one, I guess I haven't done that. Let me do that. And again, maybe at the risk of taking too long, I'll do both components or both ways. So if I say the x component of number two, I can just put in the magnitude and put in cosine of 315 degrees. Let me actually calculate that one first. So 101 times cosine of 315 degrees. That comes out to be 71.4. It's positive. Now, hopefully that matches more of the physical picture. If I were to look at the physical picture and I would say, okay, what is the x component of number 2? I would do something like this. I would say, well, first of all, the x component is in the positive direction. So I put a positive. Oh, I'll do it in green to match positive. I would then say its magnitude is 101. And then I would say I want adjacent to 45. So I would say cosine of 45. And I claim that number is the same as we got over there using absolute angles. So 101 times cosine of 45 comes out to be a positive 71.4. In fact, if you remember a little bit more about your trig functions, you could have saved yourself a little bit of work because the 45 degrees is where the sine and the cosine are the same number. That makes the isosceles triangle. So we know it was going to come out to be a magnitude of 71.4 because we did the y component. Except when we did the y component, it was down, so we got a negative. So we would have expected the same magnitude, 71.4, but in the positive, that is to the right direction. So this one is down and then this one is right. So right is a positive and down is a negative, but magnitude-wise, they're both 71.4. Okay, so again, hopefully I didn't overburden you with doing the x component two different ways, but let me put that into there. And so there's our vectors. There's our x component of number 1, it's negative, and our x component of number 2, it is positive. And they almost differ by 10. Let's see, 71.4 minus 61.1 is 10. Oh, and 3 more. I guess I don't need a calculator for that. But it's a positive 10.3, which I guess technically finishes the problem. We now have the x component of the total, and we also have the magnitude of vector number 1. I'm just going to go one more step. Maybe I'll draw it in kind of a cyan color here. But if the total vector at the end here is a positive 10, it doesn't go very far. And we already said it went up 34.5. So it looks like the result of these two is something that looks like that. The vertical one of number 1's a little more than the vertical one going down for number 2. So there's a slight upward vertical. And then also the horizontal of number 2 is slightly more than the negative horizontal of number 1. So it's just a little bit positive. So there's the result of those two vectors. And of course, the answer to the two questions. You just got to go through the mathematics of vectors, and remembering x's go with x's and y's go with y's. All right, well, like I said, hopefully that'll be helpful to somebody in terms of going a little more detail. But we were doing this one thinking this would be a great lead in to the second question that was asked. And so this is the static object with ropes. Okay, and so let me put that in my notes. Static object with ropes. And let's see, at 347. Okay. All right, so let me use that knowledge, because although that's interesting, that's just adding vectors together, and that's what you need to move forward on the, I can check this answer. 22, oh, good, yeah, it matches, okay. But now looking at this problem, this is one where we really get into the physics of it. So it says an object, and I'll just kind of draw the object here. It's got its round object. So an object has a mass of 15 kilograms. It's being held still by 2 ropes Rope number one is horizontal. So there is a rope coming out sideways, okay, to the wall. That has a tension of TW. Now, rope number two is tied to the ceiling. And so there's a kind of this overhang ceiling, making an angle of 60 degrees with the ceiling. So I'll draw a vertical line and coming across. Let me get my angle right. Here's 60 degrees. And by the way, I'll just do this as a little plug note. Notice that 60 degrees is a relative angle. It's not an absolute from the x-axis. And so like I was trying to illustrate in the problem before this, and the reason I was showing you both relative and absolute is most of your physics problems require you to think about relative angles, relative from the ceiling, relative from the wall, but not absolute from a horizontal line to the right. So we have a relative angle, and we want to think about this problem ultimately in terms of relative angles. Now, this one coming from the wall is along the positive x-axis. So this angle 90 degrees to the wall would be 0 in terms of the x-axis. So we could do absolute angles on this one, or relative to the wall 90 degrees, but I don't think that makes much sense. So I kind of see this as a mixture that we've got absolute angle here and a relative angle here. And of course, once you know one, you know the other. So it's good to have that technique to be able to kind of go back and forth. All right. Well, let's see. What did they say? And they say, and then has a tension of TC. So I guess the W for wall and the C for ceiling. Okay. And then we're asked to solve it. Now, this too is a vector problem, but it's more of a physics problem also. And so let me make what I call step number 2. And those of you who work with me, you're going to hear me say that when you do Newton's laws, take 4 steps. Step 1, get a good physical picture of what's going on. Usually you don't have to draw it because I just was redrawing what's already given there. So especially if this was a quiz, I wouldn't have redrawn this. I would have said, look, I already got a good physical picture. And my physical picture shows me that there are 2 things pulling on it, 2 ropes pulling on it, plus the effect of gravity. There's a wall and a ceiling. And a very important part of this first step is to realize it's stationary. Okay. And that's going to come back to part 3 of my strategy. But I'll say it again. Part 1, step number 1, get a good physical picture of what's going on. Step 2 is then do a free body diagram. And what we mean by that is just draw the object that you're interested in, okay, and no other objects, but draw the forces on that object. So if it is a rope, then draw the force and what you know about the rope. In this case, we have 2 ropes, but we also know gravity. So on this step where I say step 2, draw the free body diagram, I like to say this, that go ahead and draw the force of gravity. So we know the force of gravity is mg, and everything touching it. Because the other forces that don't have to touch, it's too early for you to deal with those. Magnets don't have to touch. Electricity doesn't have to touch. But we don't have any of that in Physics 121. All of our forces are either 1, gravity, or 2, there's something touching it. So I like to say, draw gravity and then everything touching it. All right. So what I have is a tug from the wall and a tug from the ceiling. And so I'm not drawing them as ropes, I'm drawing them as arrowheads. Because again, in a free body diagram, and the reason it's called free body is it's designed to help your thoughts be simplified. These problems are really hard. And a free body diagram is the first step into simplifying it, because the only thing that matters are the forces on that object. So all you need is the object and then the forces on that object. And so that's why it's good to draw this. It's going to make the next step easier. Now, of course, to draw this one correctly, you really have to have step one. So I'll say it again. Step one, good physical picture. Step two, free body diagram. Okay. And here's what step three is. Step three is to write out the equations. And since forces are vectors, split your paper and put X's with X's and Y's with Y's. And just write out your equations. And if you've done a good free body diagram, this step three, in fact, maybe I should even label them. Step one, good physical picture of what's going on. Step two, free body diagram. And I'll say it again, a free body diagram is really one to help simplify our thoughts. In fact, it hopefully simplifies it enough that it makes step three easy. Because step three is saying, look back at step two and write out the equations. Here's what I mean by that. The sum of all the forces in the x direction have to equal mass times acceleration in the x direction. And in the y direction, the same thing. The sum of all the forces in the y direction have to equal mass times acceleration in the y direction. And here's some good and bad news for you guys. Everything we do this week and next week, so for 2 weeks, can be answered right here. Sum of all the forces equal ma. Do it for the x, do it for the y. So the good news is I can make it sound that simple. The bad news is we're doing 2 weeks on this because this is hard. There are a lot of different accelerations and a lot of different things that can go on. And so we got to talk about the acceleration for each case individually. In fact, this goes back to, as I was saying earlier, I guess it was in the last problem I was doing, but I was referring back to the last video help session I was having. Looks like I lost contact here with my phone. Let me reinitiate that. I don't know why it keeps bumping me off once in a while. I wonder if there's a timer somewhere I'm missing. Used to be when the screen would go blank, that would happen.
Sometimes like when the meeting is, I don't know. Actually, no, because you probably have premium Zoom.
Yeah, the Zoom doesn't, yeah, right. I have unlimited amount of time to Zoom. But it's something about the phone. It's maybe I need to touch the screen on the phone once in a while.
Yeah.
Because it's like the phone thinks it's left on.
Yeah.
And it just goes off.
I'm surprised it went that long then.
But
that was a pretty long time, at least in comparison for like the phone being on.
Yeah. Well, I tried to put, never go to sleep on my phone.
Yeah, I mean that should have worked then if you put never.
Yeah. Okay, but anyway, let's go back to this problem here. So, all right, especially since this is the first one that I've done of this nature for you guys. I mean, I know I did the one right before this where I was just adding vectors together, but that was really more of a chapter 2 problem than it was a chapter 4 problem here, or chapter 5 problem. Sorry, chapter 5 problem. But let me say it again. I like to give 4 steps that you'll keep hearing me say this all of this week and next week, every time we do Newton's second law of motion. That number 1, try to get a good picture of what's going on. that will lead to step 2, which is a free body diagram. And if your free body diagram is done well, it makes writing out the equations really simple. Okay. Maybe simple after you've had some practice. And then the last step, what I call step 4, is the easiest of all. It's just solve the math. Which again, there I go, saying easy step. But the math can be really challenging for some of you. But I'll get to step 4 when I get there. All right, so now let's just write it out. So this says take all the forces in the x direction. All right, so let me go through every force and get the x direction. I'll start with the T sub W. Notice that this one was completely horizontal. It's completely in the negative x direction. So I would ask myself, how much force is in the x direction for this guy? Answer, all of it. So I'm going to put negative TW. The negative because it is in the negative x direction. No sine or cosine of anything goes here because this is all of it. All the force is in the negative x direction. All right, let me keep going around here. Let's go to the force of gravity. How much of the force of gravity is in the x direction? And I'm going to answer that, say none. Force of gravity is all in the vertical direction. It's all down. So just for completeness, I'm going to put +0 there. There is no force in the x direction. It is all down. All right, now let's get to the last one. And I'll say it again. We just want to go around and look at our free body diagram and add up all the forces. And the hard part is making sure we're only looking at the x component of it. All right, so I'll say it again. This first one, all of it in the negative x direction. The second one here, none of it in the x direction. Now here's the hardest one. This is at an angle. This has components. This is why we went through chapter 2. This is why I went through the video one right before this, is how to break it down into its x and y components. So I kind of need an angle here. And to get that angle, I'm going to jump up to step 1, because step 1 is the full physical picture. And it looks like step 1, if this angle was 60 degrees between the ceiling and the rope, then remembering my alternate interior angles are equal from my geometry. Ooh, hate to bring that back to you, but that's, again, it's easy to say you can do all these problems with 4 simple steps, but it's the deductive reasoning, solving the math, or in this case, going back to geometry and remembering alternate interior angles. But I'm going to use that to say this angle here is 60. And since I want the x component, I'm going to do like I did in the last problem. I'm going to do a relative angle, although in this case, relative angle and absolute angle are the same. So I guess I shouldn't make a big deal out of it. But I want, for the x component in the green here, I want adjacent to my 60 degrees. So I'm going to write this as TC and then cosine of 60 degrees. And then put a plus because it's in the plus direction. I like to say this phrase. I do magnitude, component, and then direction. And I get that by looking at the picture. The magnitude is TC, which I don't know, so I got to put it as a variable. That's one thing I want to solve for. To get the component, I would be multiplying it by a sine or a cosine. And for me to decide whether it's sine or cosine, I got to say, is it the adjacent angle? So adjacent angle would be 60 cosine. And if it's opposite, then it would be a sine function. But since this angle is 60 and I want adjacent, I did the cosine. So it's cosine of 60. Then I got to look at the picture to see, is this tugging on it in a positive x direction or a negative x direction? And it's clearly a positive x, so I put a positive. So magnitude, component, direction. All right, so that right there is what I mean by step 3. Write out the equation. I'll say it again because this is the first time. Good physical picture, step 1. Step 2, free body diagram. Step 3, write out the equation. Now, I guess I'm not completely done writing out the equation. I just went through this part of it. I guess this would be the left-hand side. I just went through all 3 forces, but then it has to equal to MA. And again, this is where a good physical picture comes into play. What would be the acceleration? Do I know anything about it from the description? And I would say, yes, I do. They said it was stationary. That means its speed is 0, and a moment later its speed is 0. That means it's not changing its speed. That means the acceleration is 0. Ta-da! All right. So this would be my equation. I would have minus TW plus TC and cosine of 60 degrees, if you remember, is 1/2. And I probably should convince you of that. Let me turn on my calculator. Let me go cosine. Let me put in 60 and hit enter. So it's not expected you remember all those special trig function angles because you got your calculator. And chances are they won't be special angles. You know, you'll get an angle like 52 degrees. And there's no way to do it other than get out your calculator or look it up in a table. Nobody looks it up in tables anymore. We get out our calculator. So that is what I mean by step 3. So there I have. I've written out the equations. Well, actually, no. I've only written out one equation. So let me also do the same thing for the y component. And not a surprise that I'll have 2 equations with 2 unknowns. So then step 4 is solving. So again, at the risk of boring you one, but kind of drilling this into your head, step 1, got a good physical picture of what's going on. Step 2, draw the free body diagram. Step 3, write out the equation. Step 4, solve the equation. All right, so let me finish writing out step 3. And I'm going to do the same thing. I'm going to add up all the forces in the y direction. And let's just go around in the same order. So I'll start with the wall, the tension from the wall. How much of the force from the wall is in the y direction? 0. It's all in the negative x direction. Okay. Let's go to the second force. How much of the weight is in the y direction? All of it. And it's all down. So it would be plus a negative mg. The negative because it's down, and of course mg is how you calculate the weight of it. And again, notice there's no sine or cosine because it's all of it. And that's kind of what I said over here for the x component. When I did this first one, I said that this tension from the wall, it's all of it in the x direction. There was no point in putting a sine or cosine here. And that's what I'm saying here. All of it is in the y direction. There's no sine or cosine. Negative because it's down. All right, so there's 2 of them. Let's do the third one. Now, the third one is probably the hard one, just like we did, back here for the x component. But hopefully that little phrase about magnitude, component, direction will work. So here's magnitude, TC. Component. All right, let me come back to the picture. For the y component, I want opposite, this vertical one, my little green triangle. I want the vertical one, which is opposite of 60 degrees. So I'm going to put sine 60 degrees. And then the direction is up, so it would be a positive. Although it doesn't make any sense to put a positive plus a positive number. So I ignore that. But that was important when I had the negative direction in the problem before this, okay? But there it is, magnitude, component, direction, okay, equals. And so I would say I've done the left-hand side, the part that I probably need to spend the most time on helping you with, because this is going to be the hard part. Write out all the forces. There it is, all 3 of them. The y component, the y component, and the y component. So the y component of each of them. Okay, what is it equal to? ma. So what's the acceleration of this one? Well, again, they said that the acceleration was 0. Now, not directly they said that. They said it indirectly. They said it was stationary, and it stayed that way. So that means its speed is 0, and a moment later its speed is 0. That means it didn't change its speed. It went from 0 to 0. change in speed is zero. That means the acceleration is zero. So if I put zero into here, I get a zero. So this equation reduces down to negative. And did they give the mass? Yeah, 15.
Yeah.
So let me put that in. So this is 15 times 9.8. Then this is plus TC. And this is sine of 60 degrees. Now, again, you're not expected to remember that that's root 3 over 2, which comes out to be 0.866. You're just expected to turn on your calculator and go sine 60 degrees and come up with 0.866. But that's a common one that we even fiddled with in the last problem. So I remember it from the last problem. All right. Now, I think the hardest step is this step 3. I've got my 2 equations with 2 unknowns. And now I can get to what I call step 4 in solving these Newton laws problems. So the next 2 chapters, chapters 5 and chapter 6, if you work with me, I'm going to keep emphasizing these 4 steps. 1, got a good physical picture, because that leads to a free body diagram. So step 2, draw a free body diagram. And if your free body diagram is done well, it'll make step 3 fairly simple, or as simple as it can be, which is to write out the equation. Just start off with the sum of the forces equal ma for both x and y and fill it in. And then once you get to this step, you will have your 2 equations and 2 unknowns. Now, sometimes these get even harder because we have 2 objects. So we would have 2 sets of equations for each object. So we would have something like 4 equations and 4 unknowns. And I got to admit, 4 equations and 4 unknowns is quite a bit of math. And so I'm going to make it sound easy. Step 4, solve the math. How hard that can be? All right, so I'm going to solve for the math. Why don't I do this? Why don't I take that first equation and rewrite it so that it says 0.5 TC equals TW. Now, why don't I use that into the second equation? Oh, wait a minute. My bad. I didn't even notice it. This is an easier problem than I gave it credit. The second equation doesn't have both variables in it. So I don't have to solve one and plug into the other. This is not a system of equations. I could just start with equation 2. So let me put this one on hold. I'll just cross it out. I shouldn't have done that one first. I should have recognized this one at first. This one has only one unknown in it. All right. So let me solve it. So 0.866 TC equals, and when I move it to the other side, I get a positive 15. So let me go ahead and go 15 times 9.8. So that's 147. And then let me divide that by 0.866 and come up with 169.7 newtons for TC. Now, with that in mind, I can come back to what I was starting to do here with equation number 1 and just say minus TW plus, and so now I can put in my TC, 169.7 times 0.5 equals 0. And if I move my TW to this side and take my 169.7 and multiply it by 0.5, I get 84, and it looks like it rounds up to a 9 newtons. And so that should be the 2 answers. And I'm learning this now. If you click on it, you can see the answers. So TC, your author here has, 170,
Yay.
and then 85. Yeah. Nice. Good.
Thanks
Yeah,
so much, Michael.
that was a really good one. I thank you for asking that one. That gave me a chance to, the first time, kind of run through with you guys these 4 steps. And I'll say it one more time. Good physical picture. Step 2, free body diagram. Step 3, write out the equation. Step 4, solve it. Okay.
Nice.
Yeah. Good. All right. Let me shoot back to the Zoom. I think I saw Anthony pop in. And I bet he put something in the chat for me. I see you still playing with your prism, and those pictures you sent were great.
I have more that are cool, even cooler.
Okay, well, keep it up. Yeah, the one thing that we as college professors and college in general needs to do a little better of is, keep students in mind that, this stuff is really interesting outside of just doing pencil and paper. And so how to keep that curiosity to keep you motivated, because sometimes going through the calculations, which is necessary, but it can become so monotonous and rigorous, and just come textbooky that you kind of forget that, I'm doing this for a reason. Maybe in your case, it's the optics, or maybe in somebody else's cases, I just working with a friend and, designing an exhaust system for the car, and you do an X exhaust, he wanted a dual exhaust system, and they wanted to switch his Y system, and he goes, do I do an H? Do I do an X? What would be better? And so we can run the calculations, and it's kind of boring doing the calculations, but there's a reason for those calculations. It's kind of exciting to see, that, hey, if we get the exhaust pattern right, depending on what you want, you can have high torque on the low end, or you can have high power on the high end.
Yeah, currently right now I'm working with my dad on a project of his, where we're trying to make a battery using latent heat. So we're using paraffin to and phase change materials to create a battery.
Oh, okay, that'd be interesting.
I'll make sure that you see it once it's all done.
Yeah, and I'd be a little curious. Phase change usually involves energy, but not an ion exchange, and you need an electron to change somewhere.
We're using it to store heat energy.
Yeah. Okay. So so you're gonna store the heat energy and then use that energy to maybe charge a battery.
Yeah, for the right now, that's one of the storing energy is really hard, and one of the ways people are using it, like there's a place in Nevada that uses super hot aluminum to store heat energy. And have you heard of that?
Yeah. I wondered, and it could very well be in Nevada too. There's a big plant, I guess it is Nevada. Yeah. You just cross over Nevada border before you get to Las Vegas. So if you're going up to 15, once you cross the California border, you get to it, and it's got 3 of them, and they use the mirrors, and they make molten. I think it was. Well, you might be right that it's a molten. Did you say aluminum? I think it's an aluminum salt.
Yeah, aluminum salt. That's what. There's one with salt. I know they use aluminum. Okay. There's paraffin is another really good one. That's why we're using candle wax. Because,
okay.
Just as a project, because it has a very, like, you can have various melting points and like different points where it changes phase.
Right.
Yeah.
Okay. Okay.
And you can't really use like water, a lot of other materials, because they either have a too low or too high of a phase change temperature, I guess.
Yeah,
I'm
yeah,
still
yeah.
learning a
Now
lot
that you bring
about
it
it.
up, that would be brilliant. If you had something that was adjustable of what temperature does the storing of energy, that would be awesome.
Yeah, right now
Yeah,
I'll send you, I'll email you some papers on it.
yeah,
Yeah, but it's really
yeah,
fun. It's really interesting to learn about.
yeah. I really like that place. Every time I drive by it in Nevada, there, it's just fascinating to see the all the mirrors shining it and uh,
Yeah,
just how hot that thing's got to be because
it's like
you
700 degrees Celsius or something at the,
yeah,
yeah,
you can't even look at it. It's glowing red hot, or not
yeah,
even. It's not even. It's so hot. It's not even red anymore. It's white hot.
yeah.
You can't even look at it. It's
Amazing.
trippy. Yeah.
But yeah, that's my view on it too. Where I mean, this stuff is it's so interesting, and especially once you like start to learn the history behind it, where Newton's like everybody thinks like Newton was crazy, but everybody like thinking Newton's crazy for thinking that the spectrum, or like that the
Oh yeah.
sunlight is made up of all colors. Like, yeah, no, that it's so interesting. uh,
Uh-huh.
and it's, to me, it's sad. It's like that a lot of the subjects that are taught are just like, um, the life kind of gets strained out of them sometimes.
Yeah,
You
yeah.
like, I mean, yeah, I like the way that you do it, because I like seeing the different ways to do it. Yeah.
Yeah, you would like this then too, I think that so that's one way. And of course what you're getting at is if you have a lot of solar energy during the day, you want to store it so that you can actually use the electricity at night.
Yeah,
Uh,
that's, yeah.
and or maybe on a cloudy day too. But there's another kind of a fun one, and the company I saw doing this was up in the Bay Area. I think it was the city of Alameda, just outside of Oakland, and they had cylinders of, and the material I don't think mattered, but it was aluminum because they said they could polish and smooth the aluminum better than any other material. Um, but it was a big cylinder of aluminum that weighed 400 kilograms, and they would during the daytime use the electricity to spin that up to a high rate of speed, and then at night they would use it as a flywheel, and they would take that kinetic energy and slowly turn it into electricity so they could run lights at nighttime for hours and hours. And then they just had a whole bank of these 400 kilogram cylinders just spinning and at some ridiculous speed. That's why they had to get them perfectly round and polished. They were just massive speeds and
It's cool. Yeah.
oh, and then so they don't lose energy due to air resistance. The cylinder goes in a container that's evacuated.
It's a vacuum. That's sick.
Yeah, and then so they don't lose too much due to rubbing. Instead of using ball bearings, they magnetically levitate it, and it's magnetic bearings.
That's crazy. Yeah.
And yeah, they said, just it would. I can't even remember how long they said it would spin if they didn't, use it to draw electricity. Once they got it going, it's in a vacuum with magnetic bearings, and it would spin for something like a week or two on its own. Uh,
That's crazy.
and
Yeah.
so they didn't have to worry about losing too much energy due to resistance if you're going to use it that night.
Yeah.
So,
Wow. Yeah. No, that's cool.
yeah.
Yeah. Storing energy is really interesting to me. I think that's probably what I'm going to try to get into. My dad's companies, like they um a lot of them deal with store, like figuring out how to store energy
Mm.
efficiently and very low cost. Um at least like sustainable energy. So right now they have one called Energy Vault. I don't know if you've heard of that. Where they lift and lower blocks.
Oh, okay.
And when they lift the block, like these heavy blocks with the tower, stores it in potential energy, and then they release it, and then as it goes down, it turns into kinetic energy. Here, let me.
Yeah. Okay. Yeah, I've seen that, and I also seen that same thing. They do the same thing with water. I've seen them pump water up a hill and put it in a reservoir, and then
it's similar. Yeah.
Yeah.
Here,
At night. Sadly, that, believe it or not, there's a lot of loss of turbulence in water. So it's storing blocks seems to be actually more efficient than storing water.
Yeah. Here, I'll show you what their company is if you turn on screen sharing. Let's see.
Let's see. So I got to stop my sharing, I think. And
you gotta enable it or something.
Yeah, there's something here. Hang on. That's not it. It must be a little side thing. There we go.
Right now I'm playing with this.
Oh, there we go. Oh, yeah, I see. Okay. Okay, here we go. All participants. Okay. Now you should be able to share.
All right, let's see. This is one of their companies. It's Energy Vault.
Okay. Yeah. Okay. Yeah. This I think is exactly the crane mechanism. Well, maybe there's more than one, but I saw something like that and then they had the study and they were showing why stacking. Yeah. I think this is exactly it. Is your dad's company?
Yeah. What's that?
Your dad's company?
Yeah, it's one of my dad's companies.
Nice.
Or at least what they do is that they're a company that it's kind of hard to explain, but they're called a startup incubator. So they have a bunch of companies that are theirs, but it's like made by they're kind of like partners with people. So they partner with people that have these ideas, but they don't really know how to get it made, or they need help getting getting the resources and the investors to come about, and like the engineers, and they have a team, we have a team of there's like a bunch of engineers that we have, and then
So is your dad the engineering side, or is he the finance side, or?
My dad's a project manager for the entire company, so he's does basically everything.
Yeah.
It's like kind of the jack of all trades or whatever.
Oh yeah, that's great. I've seen exactly this. I don't know when or where, but
yeah, they have one they're just starting to roll out. They got a big investment by SoftBank.
Okay.
So they're starting to come up, and here's my dad now. I'm showing Michael or Professor Young Energy Vault.
Hi there.
Hello.
I've heard a lot of great things about you.
Oh, well, thank you. And I'm learning a lot of great things about you too.
I don't want to interrupt too long, but I've, through my life, loved physics. I never was an expert, and I was not able to infuse TJ with the enthusiasm about it that you have. Thank you so much.
Oh, well, yes, my pleasure. You're welcome.
Have a good one.
You too.
But yeah, I'll tell them about paraffin wax.
Yeah, that's really cool. I saw this, and when I first saw this, I was fascinated. I was like, no way. And I saw the numbers at how more efficient it was than pumping water up a hill and letting it go down. Yeah,
and the great thing about it is that we're using, you wouldn't see it on the website, but we're using remediated materials. So we're taking bottom ash out of coal plants, which they're putting it in lined ponds, and they can have a lot of uglies in there, even heavy metals and things like that. And we're encapsulating those into the mass that we're storing the energy in. And so it's a big idea. Hopefully it'll work out.
Yeah.
Right, see you later.
That's great. Yeah. Talk to you later. Oh, that's awesome.
But yeah, so oops. Let me see. But yeah, no, it's really fun to because now I'm basically my office is right next to my dad's, so we can
Okay.
I can talk about ideas with him. Yeah.
Yeah.
But yeah, it's been really fun. So I don't know if Anthony has any questions. But...
Yeah, Anthony, are you still there? I tried to direct him a moment ago, and he seemed to be gone.
I got a question.
Yeah.
It's regarding the test, actually.
Okay.
On question number 2.
Yeah.
I think it's number 2. Oh yeah. Why is the amplitude for the final equation not doubled?
Oh, okay. So when you do the mathematics to get the standing wave, when you finish it up, you get a 2A, right?
You turned off your thing if you're trying to show.
Oh, yeah, yeah. Let me go back to the camera. Maybe that'd be a better way. But the short answer really comes back to, what do you mean by amplitude? And what is the math telling us in the equation? Because this equation that, there we go, I will write down, is the equation you're referring to is this: y equals 2a sine kx cosine omega t. Okay. Now, I understand the confusion in the words, because A, you might say, stands for amplitude. Okay, so if I gave you the amplitude, then this formula says double it. But there's where the confusion lies. If you actually have a standing wave, so here's the standing wave, and maybe it's this point at one moment in time, and maybe at another moment it gets to it, well, call it full amplitude. That right there is what we would call its amplitude. How big does it get?
Mm-hmm.
And that's the whole number out in front. That's everything out in front. That's the 2 and the A. So its amplitude is really, when somebody says this is the amplitude of the standing wave, what they're saying is it's everything out in front.
So the question statement was, the amplitude referred to in the question statement was the full amplitude of the standing wave.
Right. Now, if you wanted to kind of compare that, where did this A come from? Why did we call it amplitude? Well, it came from saying if you have 2 traveling waves, one to the right plus one to the left.
Now you've got 2A, both of them.
Yeah, so you might say A is the amplitude of an individual traveling wave. And so if I had stated it that way, that, hey, the amplitude of one of the individual traveling waves that make it up is 0.02, blah, 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 blah. But that being said, know this, that is really, really minor. I didn't even give it much
thought. That was the
thought.
only mistake I made on the entire thing.
Okay, and that's what I was thinking you said. So you're going to get like 49 out of 50. So, it's not a big deal to me. I just felt like I'd take 1 point off just to make sure the difference was noticed and really didn't hurt your grade. And also maybe to give credit for those who did notice, they did get then the full credit for it. So to be a little fair to them. So I only went with 1 point on it for all those reasons. So hopefully that won't be a big deal to you. So you did very well.
Good. Regarding the conversation you guys were having earlier about energy, I had seen it was like a hand warmer, but it had like a certain chemical in it.
Oh,
and
yeah.
You'd boil it. You'd boil the hand warmer and then take it out and let it like cool down, but it would store all the heat energy. and then you'd press a little button on it, and it would start to solidify. A chemical reaction would solidify it, and it would release the heat energy until it all was solid again. And then you boiled it again and melted it. It was like is it supercritical fluid? Is that what it is? When no, not super saturated, when you have like too much salt and then like you drop a piece of salt in it and it all like solidifies.
Yeah.
It was like that, but with heat energy, and it released all the heat energy.
Oh, clever.
I can't remember the name of the chemical, although I wish I could. I'll have to look it up later.
Yeah, I agree. That's clever. And I know I haven't seen it. The ones I've seen, the hand warmers I've seen, are not quite so interesting. They're just the standard chemical reaction.
Yeah, it's like it oxidizes, right? Something.
Yeah. And so
Yeah.
it just makes heat until you run out of chemicals.
Yeah, and then you throw them away.
Yeah, and then you throw them away
Yeah.
or recycle them.
This one was reusable. It would solidify. It would look like basically a block of ice, room temperature, and then it would all melt, and then you could just like store it until you needed it, and then press the little metal button, and it would kick off the reaction.
Oh, that is neat. So yeah, so you would give off the latent heat, as you said. Yeah, that's exactly the next week, or in our next chapter, we're going to be calculating and talking about the latent heat.
Latent heat. Interesting.
Yeah. Very good. That is. Yep. The world is fascinating. So
that it is.
I'm excited for you guys. So
you're going
into a great field of studies.
Yeah, I'm a CS major, but I think I might either do eventually once I transfer, might do math or physics and then minor in computer, but I don't know. There's so much that I want to do. Like I love math, like it, and the math of everything is. I might major in math because it's kind of like if you know the math of all this stuff, it like the rest of it kind of falls into place.
Yeah.
It seems like.
Yeah. Well, and computer science, a great field. I mean, that's really so many jobs are there. We just some of them are kind of mundane, but that's what we need. We need people who can tell computers how to operate and work, and we don't have enough of that. We have too many people who can draw a painting or make music, but we don't have enough who can
you're preaching
do a computer.
My sister wants to major or go to a like New York super expensive school for theater.
Theater, the arts, yeah.
My sister, she's in LA. It's called LACSA, and it's like a LA School of Performing Arts or whatever for high school. I'm like, Karen, you gotta. That's cool, but yeah, you gotta figure out what's gonna make you money while you are looking for a play job. So. Yeah,
and I don't want to turn it down. I mean, there are, obviously there is money in the arts, but there's just so many people into the arts.
You gotta be top of the.
You gotta be the top of the top. It's like being a professional football or baseball, basketball. There's a lot of money at the top, but there's a lot of people who want to be there. So most people don't end up making anything.
I spent years playing in symphony orchestra.
Okay.
I would do it now, but coronavirus.
Oh, yeah.
I think it was like 10th grade. I realized I cannot do this as a job. It won't work. You're gonna hate your life. It's not gonna work out. You got to do something else. And
can't do what?
Was the way to go.
Yeah. What was it?
So keep it as a hobby.
Yeah, symphony orchestra. I play stand-up bass.
Nice. But yeah, I think that that's why I really am interested in sustainable energy, and it's for sure the way things are going to go.
Oh yeah.
So that's why I'm like trying to get, and it's just like also really crazy interesting. So,
Well, I guess I'm real excited. I think renewable energy has turned a big corner where a lot of times we were doing it more for the environment than the economics of it. And now I think we can do, now we're at both. Now, long term, it's going to be cheaper. And of course, it's going to be better for the environment. And so because of that, it's just a huge push for all kinds of, answers and solutions and different options. I mean, I got solar panels on my house. Let's see, it was 2013. Well, I started in 2013. They didn't go up till 2014. So I've had solar panels for 6 years, and they I don't have any kind of energy storage device. That's kind of the down draw. But
Can you sell it? Can you sell the extra energy back to the grid?
Yeah.
Sell is not quite the right word.
You get like a
maybe
discount.
loan. So what happens is, so like, well, it's getting late in the day, but like earlier today, I would be making more electricity than I'm using.
Right.
And so it goes out my grid. I don't really sell it, but I get credit for it. So then at night,
okay,
when I run my lights, then it counts against my credit. And when things work right, at the end of the day, my total use of electricity is 0.
Yeah.
And the real advantage is I don't have to have an energy storage device. That's where it gets complicated, and you need like space and more cost go into how do you store this energy during the day.
That's the big money problem, or that's the big money problem to be solved. It's how do you store the most energy with the least amount of materials?
Yeah.
Because the reason why we can't store, the reason why we're trying to store latent heat is because latent heat takes less materials to store the heat energy from than specific heat, or when you have and the reason why that is because when you have, so like when ice is melting, and when all like the water stays at 0 degrees Celsius the entire time that it's melting. So until it starts to get back into like into phase change. So when you have the water, say, going from 0 degrees Celsius to boiling, that time it there's like a very different temperature throughout. So you would so like say if you're powering something with heat energy, there would be less energy at one point than there would be at another. So the balance, trying to figure out how to balance the amount of energy takes up more materials than if you say store it while it's going from liquid to, or going from solid to liquid.
I see that. No,
that's from my understanding, from a very basic understanding of it. My dad's the expert on all this.
But like I said, that's kind of the exciting thing. There's just so many different potential options to be investigated. That's a fascinating future.
Yeah. I got to get going. Thanks so much, Michael.
Sure.
Yeah, this was really nice to just like hang out and do these problems. Yeah. And
all right.
You did really in depth. So.
Okay, good. Yeah, and I'm glad I got through those. Can't wait to send those out to the other you guys in 121. So, but I think I'll get something to eat before that. I'm getting hungry. Yeah.
I need to get something to eat too. I'm pretty hungry.
All right.
I haven't had lunch today. I just have been working all day. But yeah, it was nice to meet you too, Anthony.
Yeah.
What class are you in? 122?
123.
Nice. Awesome. Well, I'll talk to you guys later.
Okay, yeah, you guys, I guess, will be in the same class next fall. You'll be
We
in
will?
122.
No, I took 122 already.
Oh, I'm sorry.
I
I,
was with you last semester.
yeah, okay. I was thinking I was helping you in 121, but they all mixed together. Oh, no,
Yeah.
that was Daniel. You
Yeah,
and
that
Daniel.
was well, me and Daniel were here like pretty much at the same time every Friday.
I know, and I keep mixing you guys up, and I still do. Which one was 121 and which was 122? All right.
Yeah.
So
Hey, you
got
see
that
this-
wrong.
I got the spectrum on my arm.
You do.
All right, Dr. Young.
All right, talk to you guys later.
Next Friday.
All right. See you guys
Have a good
later.
one.
Bye.
Thanks, Michael.